We will start with Konrad Patkowski. So Konrad Patkowski is a professor of physics and chemistry in Auburn University, Alabama, in US. He graduated in Warsaw, so actually he's an alumni of quantum chemistry laboratory.
Same group.
Yes, the same group. Actually, we overlap for some time. So Konrad, please.
All right, so this is welcome everybody. This is a workshop, so stop me at any time. And this workshop is meant to cover the basics of SAPT and how to run Psi4 software to get some SAPT results. So if you're an advanced SAPT user, I hope you brought something interesting to read for all of these parts where this is nothing new to you, and hopefully every now and then there will be something interesting. So a couple acknowledgements that are due. So Psi4 is the software that we will be using to run our simple SAPT calculations on our laptops today. But of course, Psi4 can do much more than that. And it's something that if you are running SAPT, then quite likely, not exclusively, you will be running Psi4. This tutorial is modeled on the excellent resources of MolSSI, who is also an associated partner of PhiMol. And from what I heard, during one of your later PhiMol workshops, there will be people from MolSSI itself helping you out with best practices coding in Python, which is also a great resource. So Psi4 Education is an outreach of education part of Psi4, and I'm saying we because I made a small contribution, have created educational modules for students with a version for teachers as well on various aspects of computational chemistry that are in the same form as we'll be using today, in the form of a Jupyter notebook. So the notebook that we will be going through today is actually a modified exercise from Psi4 Education that I wrote some time ago, and now for the purpose of PhiMol, I added more functions so that we can go a bit deeper into different capabilities of SAPT. Now we'll be using a very simple program to visualize some densities and orbitals in our Jupyter notebooks. The program is called Forte Cube View, and the author is Professor Francesco Evangelista at Emory University. And Forte Cube View doesn't have a logo, but it's a part of the bigger Forte ecosystem of code. So that's what Forte is doing here. And NSF and Auburn University are supporting my group. NSF is the US National Science Foundation, of course. So I do live in the United States, in the state of Alabama. That's the one highlighted in there. And Auburn is this dot. It's a small town, 80,000 people, a lot of college students. As you see, it's in the south, so it is warm out there, especially in the summer. So we started the workshop with a very warm day, or especially Monday was really warm. So that's the typical summer weather. But fall and spring are very, very nice, and the winter is very mild. So I think a few of you will come to Auburn for some time as part of your PhiMol doctorate. So I will welcome you with open arms. That's a great little college town. That's just an aerial view of campus, the more historical part. But the chemistry department is a little out of the picture, but it's definitely very walkable. So enough about Auburn, and we want to run some SAPT. So first, why SAPT? So what kind of goal are we addressing? First, let me put on a broader and easier goal to satisfy, as we're all interested in intermolecular interactions, in general in weak interactions. So we'd like to get the numbers right, and we'd like to understand the numbers. So let me put the goal in this form. So we'd like to see a method that gives accurate interaction energies or gives insight to the nature of interaction. And as long as there's this or in the middle of the sentence, we have plenty of good choices. So if we want some method to get the right numbers, the accurate interaction energies, the most typical approach would be the supermolecular method that follows the very simple idea that I just need to run 3 calculations using our favorite software and favorite electronic structure theory. First, I'll build a supermolecule AB, so all the nuclei of A and B in their places in the complex, calculate the total energy, and then subtract the energy of molecule A alone and energy of molecule B alone. What's left is the interaction energy. Is it an accurate interaction energy? Well, it depends on how you calculate it, and today we'll also make a couple attempts computing interaction energies like this, and some of our numbers will be accurate, some will not. So depends what you're using, but if you employ a high accuracy electronic structure theory, such as something from the coupled cluster family, CCSD parenthesis T, or maybe even for small systems CCSD-T parenthesis Q, then you will get really good interaction energies this way, really accurate numbers. And there's quite a body of work, especially from the group of David Sherrill, that benchmarked various combinations of the coupled cluster level and basis set to define, I'm sure you've heard people talking about CCSD parenthesis T as the gold standard of quantum chemistry. But of course, the accuracy depends on what basis set you use as well. So they designed a more approximate levels that it's still CCSD parenthesis T, but small basis, so that's not enough for gold. We can call it the silver standard, that it's still reasonably accurate. If you want to go beyond gold, there's a platinum standard, then you need to do something like CCSD T parenthesis Q. But in general, if you have a powerful computer and time to spare, there are ways to get very accurate numbers for the interaction energy. Can you use DFT? Yes, but as usual with DFT, your mileage may vary, and definitely you need to account for dispersion in some good way. And then also it's very important before you start running your functional on a large scale to benchmark it to find out if it's doing good for the kinds of systems that you're interested in. And again, there's plenty of large benchmark studies that compare the interactions of the accuracy of different density functional plus dispersion variants on a large number of non-covalent interactions, such as this study from the Head-Gordon group. Now, that's kind of easy and well established for small systems. Interestingly, if the systems get bigger, even if they are still like, well, closed shell, single reference, you can have some issues. So you run into some inconsistencies of the benchmark, as actually our host has shown, Alex's group, that some of the benchmarks that you get from CCSD parenthesis T don't necessarily agree with quantum Monte Carlo benchmarks. So there are still some remaining problems, but overall, that's if you have enough computer power, that's a great way to get an accurate number, an accurate interaction energy. This is a number, one number, so it doesn't tell you a lot of what's going on in the interaction process. So if you want the second part, if you want some insight to the nature of interaction, you need some kind of energy decomposition. So you need more than one number. You need separate pieces that correspond to different physical aspects of the interaction. So there's a whole range of energy decomposition analysis methods dating back to the seminal papers of Keiji Morokuma, where you represent the interaction energy as a sum of different terms corresponding to frozen density, polarization, charge transfer. In general, these approaches are variational. So in a variational method, if you make the model space bigger, so if you allow for a function from a larger space, your energy will get lower and you will capture some additional effects. So if you make the space bigger, so relax the wave function, you can get a new term, and if you do it gradually, you can get the interaction energy piece by piece. Now, this provides a valuable insight into the nature of interaction, but most of the existing EDAs are based on fairly approximate methods, such as Hartree-Fock or DFT. You usually get dispersion as an afterthought in these methods. Well, there's some newer versions of Head-Gordon's approach have dispersion built in, but still it doesn't really get better than MP2. So if you want a method that gives accurate interaction energies or an insight to the nature of interaction, you have plenty of choices. But I want a stricter condition. I want a better method that does both at the same time. And now your options suddenly get quite limited. Before I get into SAPT, which is obviously my favorite answer to this call, I should mention the method of Giovanni Bistoni based on the decomposition of local coupled cluster. It definitely, since it adds up to a coupled cluster interaction energy, the total interaction energy is accurate, and the splitting is more mathematical than chemical, I would say. So it's different, but it does provide interesting and valuable insight into the nature of interaction. But of course, SAPT is my favorite approach, and some other people in this room, we have worked with SAPT for quite a while. And there's this seminal review paper by the main authors of SAPT, Bogumił Jeziorski, Robert Moszyński, Krzysztof Szalewicz, the classic chemical reviews. But if you want to find out what's new in SAPT and some of the recent developments, I do recommend the review that I wrote for Wires in 2020 that really had pretty much everything that was new up to this point, but it's still an active theory. So recently, Michał Chapka and several others, we have written a review for the special issue of Advances in Quantum Chemistry about Polish quantum chemistry. So some brand new developments in SAPT are out there. So that is definitely some good further reading. And overall, there's plenty of references around here, but this PowerPoint will be available to you. So if you will need to find go back to some specific resources later on, that's what it's meant to provide. So the main idea of SAPT. So we have a perturbation theory, so we have a 0th order Hamiltonian and a perturbation. And in the context of SAPT, the 0th order Hamiltonian, and I think I can probably turn the laser pointer, all right, is the sum of the Hamiltonian for molecule A and molecule B, and then the perturbation, so the rest is actually the intermolecular interaction operator V. So all the Coulombic interactions between nuclei and electrons on molecule A with the nuclei and electrons on molecule B. So some of these terms will be attractions, nucleus, electron, electron, nucleus. Some of these things will be repulsions, nucleus, nucleus, and electron, electron, and the balance of it is the intermolecular interaction operator. And as usual in perturbation theory, I put this perturbation parameter lambda in front of it, and I will be looking at the convergence of the series in powers of lambda. So I have to start with the 0th order energy and wave function. So the 0th order energy is very simple. That's the sum of energies of two molecules, so when they are non-interacting. The 0th order wave function is maybe too simple for its own detriment. It's a product of the two monomer wave function, and then, as usual in perturbation theory, I try to account for the interaction for the perturbation in the form of a perturbation series where I expand both the wave function and the energy in power series of lambda, starting from the 0th order wave function and then getting the 1st order, 2nd order corrections to both the energy and the wave function. And hopefully I don't have to go too far, and just a couple low order corrections will be enough. So that's the main idea. Now if we try doing it just like that, we immediately run into two very serious issues, and we have to do something about it. The first one relates to the fact that we've all heard that the perturbation theory works well when the perturbation is small, in quotes. Is our perturbation small? Well, depending on how you look at it, I guess you might say that if the two molecules are far away, then this interaction operator is really small. But I like to look at it in terms of what does this interaction operator do to the wave function. And it actually does a lot, because if you compare the true interacting wave function, psi, and psi 0, the 0th order wave function, they look very different. because psi has to be anti-symmetric if we exchange any pair of electrons. But you see that psi 0 is a product of two anti-symmetric functions, so we can exchange electrons inside a molecule, but it doesn't have any definite symmetry if we try to exchange a pair of electrons between the molecules. So these functions look very different, and this means that this perturbation theory needs to account for a very big change in the wave function. And in practice, the result of it is that if you try naively doing this perturbation theory, your molecules will not repel at short range at all. You will not get the exchange energy of the interaction. And that's really bad. So we have to solve this problem. And the solution of this problem is symmetry adaptation. So this is why it's symmetry-adapted perturbation theory and not just perturbation theory. And the symmetry refers to the permutational symmetry of the wave function. So we could imagine that perhaps because the parts of the wave function don't have the right permutational symmetry, we need to apply to them a symmetry projector, an anti-symmetrizer, to make them anti-symmetric. And that's the general idea of SAPT, the symmetry adaptation. Now there's more than one SAPT. We can do it in several ways, depending on where exactly do we throw in the projection operators. And the different SAPTs in general can be divided into two groups: the strong symmetry forcing, where we explicitly anti-symmetrize the wave function, and the weak symmetry forcing, where we don't touch the wave function and only symmetrize the energy corrections. And you can imagine that strong means that probably we get a method with better properties, but it's going to be harder to implement and run. And weak is probably easier, but not necessarily as good. So what do we do? Well, in all practical calculations, we do the weakest of the weak symmetry forcings out there. So the so-called symmetrized Rayleigh-Schrödinger approach. So any SAPT code that you might have seen is based on SRS. That's the weakest symmetry forcing possible. We only symmetrize the energy corrections, and only at the end when we run out of other options. But that actually works pretty well, and you do get all of the exchange terms. And now your two molecules don't try to fall one on top of the other, so you get reasonable potential energy surfaces. So this problem has been solved, but we have another one. So I was very optimistic when I wrote this formula for you, because perturbation theory assumes that you can solve the problem for the unperturbed wave function, so that I can find the best solutions for the Hamiltonian HA plus HB. Or in other words, that I can do full CI for the two molecules separately. Well, usually I cannot do that. Full CI is, as we know, a very expensive approach. So usually I cannot obtain psi A, psi B this way, and I have to resort to some approximations. So what I can do for much, much bigger molecules is perform a Hartree-Fock calculation and obtain a Slater determinant for A and for B. And if I can start my SAPT from Hartree-Fock instead of full CI, then definitely that's going to be a much more practical method. So that's what we do. So instead of the true exact wave functions for the non-interacting molecules, which we cannot get if we cannot afford full CI, in other words, we cannot get, we start from the monomer Hartree-Fock determinants. And now, of course, we're missing something important. We're missing electron correlation inside the monomers, so inside each molecule. So now we'd like our SAPT to recover not just the intermolecular interaction, but also how this interaction is affected by the intramolecular electron correlation, because that's definitely something that our zeroth order wave function is missing. So how do we do that? We do a double perturbation theory. That's historically the first approach to solving this problem. And we write down the Hamiltonian as the sum of monomer Fock operators. Well, that's a good zeroth order Hamiltonian because we can solve it. We can get all of the occupied and virtual orbitals for A and B. And now we have two perturbations. One of them is the same as before. That's the intermolecular interaction. And the second one is the sum of whatever we're missing in the Fock operator, which is formally called the Miller-Plesset fluctuation potential. That's the same thing, same perturbation as you have in your MP2 or MP higher order for each molecule. So that's the effect responsible for intramolecular electron correlation. And because you have a double perturbation theory, you have a double power series, and now your interaction energy becomes a double sum. And the individual SAPT corrections are labeled by two numbers, m and n. And m is the order in the intermolecular interaction. N is the order in the intramolecular correlation. We already know that we have to symmetry adapt, and thanks to symmetry adaptation, each part will have each SAPT correction will have two parts. The so-called polarization part, which is what you get without the symmetry adaptation, and exchange part that only arises when you force the proper symmetry. And please note the range of summations. So the corrections for the intermolecular interaction start from the first order. We're not interested in the non-interacting part. That's not the interaction energy. But the index that shows the order in intramolecular correlation starts with 0, because we want to have the non-correlated effects of the interaction plus some higher ones. So that's the general notation, and I think that's a great place to look at what do these lower order corrections mean. Because first, as usual in perturbation theory, we will not calculate 500 of these corrections, only a couple, lowest order, and hope that that's enough. And second, the promise that I made for SAPT is that we can get an insight into interaction energies. So we're getting a bunch of numbers, and what do these numbers mean? So I'll try to illustrate the meaning of the lowest order SAPT corrections with some seriously bad and crude cartoons. And in the first order, thanks to symmetry adaptation, I'm getting two pieces of interaction energy. I'm getting electrostatics and exchange. And I skipped the second index because I can do anything. I can just look at E10, or I can look at corrections due to intramolecular correlation. And in general, the interpretation is the same because that's the same component of the interaction. So this first part, electrostatics, is the simplest term where the densities, the electron densities of the two molecules are exactly as they were without interaction. So the molecules have not been affected by each other, the densities, but these densities interact coulombically. Both the nuclei and electrons of A interact with the nuclei of electrons of B. Now, if the molecules are very far apart and the densities don't overlap, we would probably use the multiple expansion to understand what's going on, and maybe, for example, for two water molecules very far away, we would decide that this interaction is dominated by the dipole-dipole interaction, because each of my water molecules has a dipole moment. But SAPT is not limited to these very large distances. SAPT is totally fine when the monomer densities overlap and the multiple expansion breaks down. In other words, the SAPT in all corrections, not just electrostatics, can account for the effects of charge overlap or charge penetration. So the stuff that is not there in the asymptotic long-range expansion, but requires the densities to overlap. So that's the first part, and my bad cartoon indicates that the two molecules A and B are in their original non-interacting state, and these two charge densities interact. Now, we need symmetry adaptation to get exchange. This is where it's coming from. And actually, the first order exchange is a repulsive contribution, and that provides the main source of short-range repulsion. So this first order exchange is the main reason why your two molecules cannot get too close to each other. Now, what happens if we go to the second order? Interestingly, the second order correction naturally splits into two different pieces, both for the non-exchange part and the exchange part. And we get quite a long-reaching interpretation. The first part is the induction energy. And induction energy comes from the classical polarization. So one molecule, such as B in this cartoon, generates an electric field. And this electric field reaches the molecule A and polarizes it. So the electron density of molecule A gets shifted around. And now this polarized molecule A interacts with B differently than the non-interacting non-unperturbed molecule A would. So we have the effect of polarization of induction. It's pretty easy to see that I could take a mirror image of this cartoon and get another part, because just like B can polarize A, in the same way the molecule A can polarize B, and that's the other part of this induction energy. So both of these appear together in the second order, but you can split them if you want to. The dispersion energy, now this is a purely quantum mechanical effect, and moreover, it's the purely electron correlation effect. So this is the effect of intermolecular electron correlation. So if the charge distributions of the two molecules fluctuate, these fluctuations are not independent of each other, but they're correlated, and this results in the energy lowering. And that's the dispersion energy. And dispersion energy is, for example, the main binding force between noble gas atoms. So the London dispersion forces, and dispersion energy is your reason why you can have liquid helium at very low temperatures. So there has to be something that holds these atoms together, and this is what holds these atoms together. And now, as you see, we have two other parts, and these two additional parts, the exchange. So there are two effects that are both repulsive, because induction and dispersion are attractive. And these two exchange corrections, exchange induction and exchange dispersion, are responsible for quenching induction and dispersion at short range, so that the polarization molecule, when polarizing, doesn't get overexcited and doesn't polarize too much, so that the densities get too close to one another. What if we go to third order? We don't always go to the third order in the intermolecular interaction in SAPT, but when we do, this is what we get. So we actually get a sum of 6 terms. 3 of them, as you see, involve exchange, and 3 of them don't. So again, every piece has its exchange counterpart. And we have pure induction, mixed induction dispersion, and pure dispersion. And using our cartoon style, we can represent all of these. Now, pure induction, interestingly, has 3 terms. The first 2 are kind of similar to second order induction, except that this molecule that's polarized, I gave it a more complicated shape because it's polarized to second order, or let me use a word that's probably not in English language, but it well reflects what's going on. This molecule is hyperpolarized because this is related to the hyperpolarizability of the molecule. So one unperturbed molecule B hyperpolarizes molecule A, and vice versa. But you have a third term that's quite different, where each molecule polarizes the other one, and now the 2 polarized molecules interact with one another. There's no electron correlation required there to get that. That's a pure induction effect, but we get it in the third order. For the mixed induction dispersion, it's very much what the name suggests. So in the induction energy, one molecule polarized the other. And now this polarized molecule also wants to have a dispersion interaction with the original one. So now there's intermolecular electron correlation between polarized molecule A and unpolarized molecule B, and vice versa. And the pure dispersion term in third order is actually it's a small term, and it's a repulsive term. So it modifies the second order dispersion, accounting for effects of higher order electron correlation. So that's the interpretation in low orders. And as you see, because we're getting every term separately, we can understand what's going on in this interaction. But of course, we have a double perturbation theory, and potentially we have a lot of corrections. So we have to decide, where do we stop? So the earliest place we can stop, and the most approximate level of SAPT, is called SAPT 0, or sometimes SAPT HF for Hartree-Fock. And as you see, we just take those corrections, and all of them have a second superscript of 0. So in SAPT 0, we ignore intramolecular electron correlation. That's the interaction of Hartree-Fock level molecules. And when it comes to the first index, the intermolecular interaction, we stop at 2. So we do the induction, dispersion, exchange induction, exchange dispersion, but we don't go to the third order. There are some subtleties to make the results more meaningful. So the induction and exchange induction correction have this additional subscript resp for response, or for the relaxation of Hartree-Fock orbitals. So if you've ever performed some calculations for a molecular property, such as a dipole moment or polarizability, chances you run something similar to coupled perturbed Hartree-Fock calculations to make sure that the orbitals relax. So this is what you need to do to get this slightly better induction energy. And finally, you add the term that's personally my least favorite, but it's usually there. It's coming from a supermolecular Hartree-Fock interaction. So if you take the Hartree-Fock interaction energy, just calculate it with 3 Hartree-Fock calculations for the complex and for A and for B, and you subtract the terms that we already have from there, so the sub-zero terms in the Hartree-Fock interaction energy, so everything that doesn't have electron correlation. Electrostatics, exchange, induction here doesn't have electron correlation. Dispersion does, so we don't take it here. This effect, in principle, should account for higher order induction effects and exchange induction. In practice, it does account for these effects, but it also has some spurious terms. So it's not ideal, but for more often than not, it helps, so people use that. And that's sub-zero. And since it's the simplest level, I don't expect miracles when it comes to the accuracy of this approach. That's going to be fast. An easy way, but it's only qualitatively accurate. So it won't give you something very unreasonable, but you will not get very precise numbers. So my favorite application of sub-zero is just, does this equation has intramolecular interaction in consideration? Here, there's no intramolecular correlation. So it doesn't. So this, at sub-zero, is the interaction of 2 Hartree-Fock level molecules. If we want intramolecular correlation, we have to do better than sub-zero. And we will do that very soon. So if you just want qualitative accuracy, one great application is, for example, to classify complexes according to the interaction type. So I have 100 complexes in my data set. Which of them are mainly dispersion bound? Which of them are mainly electrostatics bound? I can take a look with sub-zero, and I can represent the conclusions on a ternary diagram, where the position of a point tells me the relative importance of the 3 possible binding forces: electrostatics, induction, and dispersion. The color is just for visual effect, so it doesn't mean anything in here. But for example, every dot represents one complex. So a dot around here, a red dot, represents a complex that's bound primarily by electrostatics. Go ahead, please.
I'm sorry, I missed this, but if we get to tell the Hartree-Fock term and plug it back in, we just get the total energy with Hartree-Fock plus dispersion correction.
That's absolutely true. So sub-zero can be also represented as supermolecular Hartree-Fock plus dispersion plus exchange dispersion. Now, I still prefer writing it this way because I get more terms and I can interpret each one of them separately. But you're 100% correct that that's exactly equivalent to something that was already known as Hartree-Fock plus dispersion.
If I may just comment, if you say Hartree-Fock plus dispersion, it's not always clear with what
dispersion. Absolutely. So that's Michał is absolutely right, because you can try to add a different dispersion to Hartree-Fock, but you are absolutely right that this is Hartree-Fock plus some particular account of dispersion given by these 2 terms. And dispersion, once again, it's purely electron correlation, so Hartree-Fock has no dispersion, so definitely we have to add this. So these ternary diagrams illustrate the makeup of some popular databases. So S66 times 10 is actually just a tiny extension of S66 times 8. So one of the famous data sets from Jan Rzezacz and Paweł Hobza. Now Jan has all kinds of new data sets. So he will be talking about it later today because Jan is in town. So now they have a better coverage, but as you see, this is how we can represent their data set. Now, this is a bigger data set from the group of Rob Distasia at Cornell University, a pretty recent one. And in particular, they got close to this corner, so systems bound by pure induction, and all of these systems involve an ion as one of the monomers. So an ion interacting with some kind of molecule, that's how you can get there. So if you don't need cold hard numbers, just you want to approximately understand what's going on with this system, SAPT0 is a quick calculation. And you can make nice ternary diagrams like this. We're going to make one today. But
The plus and the minus of electrostatics?
all right, so electrostatics can be attractive or repulsive. The best analogy is if you think about two water molecules and their dipole-dipole interactions, the dipoles can be oriented favorably or unfavorably. So we have to have two triangles in our ternary diagram, and if the electrostatics is attractive, we are in this regular triangle, and if the electrostatics is repulsive, we're somewhere in this inverted triangle.
So it depends on the orientation.
Depends on the orientation of the molecules. So as you see, because this database has potential energy curves going through the minima, so it only has favorable orientations. But if you made a similar graph for the entire potential energy surface, which we're going to see later today, then we'll have points all over the place. So that's my favorite use of SAPT0, because it can... Yes, Alston, I see you have a question.
I wanted to make two comments on pure nomenclature.
All right.
Yeah. The first is one which has caused confusion, well, it's both caused confusion in one way or another. One is this use of pole. In the original SAPT, if you go back a few slides, you can see the SAPT interaction as the polarization part plus the exchange part. And I quite often have had to explain to people that this does not mean it's the polarization energy. Because that's one, maybe you could explain how it came about. But the other one which still causes confusion, and in fact we had a discussion yesterday where I realized is when you refer to SAPT as an energy decomposition method, it sort of seems to imply that it's decomposing some kind of energy. And I've had referee reports where people have said you can't be SAPT DFT cannot include dispersion because DFT doesn't include dispersion. Now, so you know, my preferred choice would be energy component analysis, if you wish, so it's not decomposition, and that would then include things like ALMO or SAPT under one umbrella, without leading people to believe that it's decomposing something. Now, I know this is not completely true because once you include delta Hartree-Fock, things get a little weird. But what I mean. Maybe you could just comment on these two.
So yeah, I'm glad that you bring both of these. So first of all, on the first one, a complete agreement from me. So I try not to overuse the notation pole, and I think I said today non-exchange contributions, trying to weasel away from using that word, because I do like when the polarization explicitly refers to polarization, so induction. That's just the original nomenclature, where in this original nomenclature, pole means just everything that's not exchange. So that's like a very wide umbrella, so including electrostatics, induction, and dispersion. So everything on this ternary diagram. Why is exchange not on ternary diagram? Because it's repulsive, and it's not the reason that things bind together. And the second point, so the energy decomposition analysis, again, has a very specific meaning in quantum chemistry. And SAPT is not an energy decomposition analysis, but we can decompose and analyze the interaction energy. So I do apologize for the confusion it generates. But definitely the analysis of interaction energy components and contributions is a bit more to say, but it's a more precise description of what's going on. But please go back in your mind to where we started. So we wanted a method that gives us an accurate total energy and meaningful components. And that's what SAPT can be. Maybe not SAPT0, but we need to do a bit better, but that's what SAPT can be. So we get the components separately, and that's how we can interpret the interaction energy. So it's not the same as EDA. There was a question from WebEx, why is Hartree-Fock in the induction energy? So again, this comes from an approximate interpretation of what's there in this delta Hartree-Fock, and the main part, at least the desirable part of what's there in delta Hartree-Fock, is higher than second order induction and exchange induction. Well, we don't definitely there will be no dispersion effects in delta Hartree Fock because it's coming from an uncorrelated method. So among these four basic fundamental kinds of interaction, definitely delta Hartree Fock is most suited for induction. I'm not going to go as far as to say that it's truly 100% induction, but that's where we lump it in. All right, so that's sub-zero. Let's go beyond sub-zero. So how do we make our numbers quantitatively accurate? How do we make our... So what do we do? Well, there's several strategies. The first one is to continue our double perturbation theory further and include some stuff beyond sub-zero. So terms that involve intramolecular electron correlation or maybe higher orders of intermolecular interaction. And you usually add several things at the same time, and depending on where you stop, you get methods with different names that are called levels of SAPT, and you can go from SAPT-0 that just contain, apologize that the particular corrections are not readable, but just you get the idea that SAPT-0 is the basic set of corrections. Now you add some stuff, you get SAPT-2, you add some more, you get SAPT-2 plus parenthesis 3, SAPT-2 plus 3. All of them are available in the software we'll be using, and these are higher, and they of course are more expensive than SAPT-0, but at the same time quite a bit more accurate. So you can include various higher order SAPT corrections, and many of them have the effect of intramolecular correlation indeed. So for electrostatics, I know you can't read those numbers, so let me read them for you. This is E12 electrostatics. So second order correction due to intramolecular correlation, and there's an E13 electrostatics in here. But also there are some effects such as here E30 dispersion. There's this third order dispersion that also gets added in some of these higher levels of SAPT. So that's one possibility if you want more accurate interaction energies and you have a powerful computer. The other possibility that's in no small part to the work of Alston Mesquida is SAPT-DFT, which is an alternative to wave function-based SAPT, where we realize that a good way to account for intramolecular correlation, which is short range in nature, could be to use density functional theory for the individual molecules. So we can use Kohn-Sham orbitals and orbital energies in place of the Hartree-Fock ones, and the theory would look very similar because we still have one determinant. We just have a different set of orbitals, and we can just throw it in the formulas for the SAPT corrections. So this leads to the method known as SAPT-KS, SAPT Kohn-Sham, that I think has two very important potential advantages and one big disadvantage. So let me tell you about them. So I think the promise of this idea of SAPT-KS is that we know that DFT does some things well, like geometry optimization, individual molecules, short range electron correlation in general. And DFT does some things very poorly, dispersion, long range correlation. So let's stick with DFT. Let's make DFT do what it does well. And for the tasks that DFT is known to fail, we outsource those to SAPT. And that's how SAPT-KS works. So we need DFT to account for the short-range intramolecular correlation and not for the intermolecular interaction. So in principle, that's a great idea because we use DFT for what it's good at, and we use SAPT for what DFT is bad at. And the second big promise of this method is a much more computationally efficient approach than what you have with, say, SAPT-2 plus parenthesis 3, where there's a lot of expensive corrections to calculate. Because a lot of these corrections in SAPT-2 plus 3 are for intramolecular correlation. But if we do SAPT-DFT, we trust that DFT can take care of intramolecular correlation. And in fact, we just calculate the SAPT-0 like corrections. The second superscript is 0. We don't worry about like the Kohn-Sham equivalent of Miller-Plesset fluctuation potential. We just ignore this stuff. We trust Kohn-Sham to account for this intramolecular correlation. So I think that's a big promise because we can in principle get an accurate method and a very computationally efficient one. I guess there's just one problem, that as written, it doesn't work. So thanks to the work of two groups, Andreas Hesselmann and Georg Jansen, and Alston Mesquida and Krzysztof Szalewicz and Bogumił Jeziorski, there were two important problems that needed to be solved before SAPT-KS turned into a method that's practical and accurate. And their problems were so fundamental that the new approach that we got, we couldn't even call it SAPT-KS anymore. We need a new name. So that's how we get to SAPT-DFT. And we need these two improvements to become an accurate and robust approach. So the first thing, we have to take care of something that you never worry in simple supermolecular DFT calculations, but here you have to worry about, is the asymptotic behavior of the exchange correlation potential. So the true exchange correlation potential for the electrons of spin sigma should vanish asymptotically like the inverse first power of the distance, far away from the electron density, but there's a constant, there's the constant that shifts that involves the negative of the ionization potential plus the energy of the highest occupied molecular orbital. And all your favorite density functionals fail miserably on this condition, so the long-range behavior is nothing like that. They don't even go to zero correctly. So you can do two things to make sure that your exchange correlation potential is asymptotically correct. You can either correct it or use one that's asymptotically correct from the very start. So the first approach leads to the so-called asymptotic corrections, like Fermi-Amaldi or Grab asymptotic correction, where you splice with the long-range exchange correlation potential that goes to zero, and then you supply this number in parentheses to shift it to the right place. And the second approach is use a long-range corrected functional, so the ones where there's a range separation parameter, and now you have to be very careful to select your range separation parameter correctly, and there are some appropriate approaches for tuning this range separation parameter separately for each monomer. So that's critical to have the asymptotically correct theory. And now that's still not enough for dispersion. If you go ahead, Alston, I see.
I just want to make a comment here, in case people are wondering why this is even important. The asymptotic form of the exchange correlation potential has a direct effect on the density tails. And the density tails are what we need to get right for intermolecular interactions, because that's where the overlap happens. So if you mess the density tails up, the density overlaps go wrong, the electrostatic energy goes wrong, the exchange energy goes wrong, and honestly everything else above it goes wrong too, for similar reasons.
Yes, I think here the SAPT-KS would become a victim of its own power, because you don't have to worry about it if you do supermolecular DFT, because the tails are wrong, but you do these things wrong anyway. But the SAPT-KS has the potential to get all of these long-range terms right, but it has to be fed the right density tails. So, thank you, Alston. I appreciate that. So you know what's the second thing is going to be? We need to fix dispersion. So the dispersion from SAPT-0 would correspond to the uncoupled polarizabilities at long range, or would overlap the response function called FDDS, or frequency-dependent density susceptibilities for molecule A and molecule B. They have two positions and a frequency, and we integrate over the imaginary frequency. And this formula, called the generalized Casimir-Polder formula, gives you in principle potentially the exact dispersion energy if you plug in the proper FDDSs. And if you don't do anything special, so just pretend that you're doing Hartree-Fock-based SAPT but with Kohn-Sham orbitals, you don't get the right FDDSs, so you actually have to do the proper DFT linear response theory. So your approach is very similar to TD-DFT, time-dependent DFT, to get these frequency-dependent density susceptibilities at imaginary frequencies. Do this integral, and this is the way you get the meaningful and accurate dispersion. And when you do these two things at the same time to SAPT-KS, you get a method that's called either SAPT-DFT or DFT-SAPT. There are two names for the same thing. They're essentially equivalent, and that's the useful variant. That's the robust variant. That's actually the powerful one. So these were the two solutions to the fundamental problems of SAPT-KS that led us to SAPT-DFT. So how accurate are these things? So there's a bunch of great studies from David Sherrill's group that look at accuracy of different combinations of SAPT variant and basis set on a bunch of popular databases, such as this S66x8. And here there's just an excerpt from one of the papers of David Sherrill. At the bottom part is relative computational cost for some particular system. So SAPT-DFT is here. It's more efficient than this like higher level wave function based SAPT, and definitely more efficient than supermolecular coupled clusters, and pretty accurate, although you can get a bit better with wave function based SAPT. So starting from SAPT-0, it's only qualitatively okay. It's actually not in this picture. It would be worse than stuff in this picture. But because SAPT-0 is missing some important terms, especially with dispersion, you get a little paradoxical behavior, is that it's a bad idea to use a large basis in SAPT-0. It actually relies on error cancellation, and if you use a small basis, and this June CC-PVDZ works like charm. It's for no very fundamentally good reason, but you get a very consistent error cancellation, and you get reasonable results from SAPT-0. If you go to complete basis set limit, your accuracy goes down dramatically, because you're missing some important theory level effects, especially in dispersion. So if you go beyond SAPT-0, we can approach the accuracy of supermolecular coupled cluster and sometimes surpass the accuracy. So that's the promise I made with SAPT. We can get very accurate interaction energies, just like coupled cluster. But coupled cluster gives us one number, and I got like 10 of these numbers or more, so that I can interpret. Each one of them is related to some physical aspect of the interaction. So I get accurate total energies and insight, not or, but and. That's the power of SAPT. And David and his group established, just like for coupled cluster, gold, silver, and bronze levels of SAPT. So depending on the target accuracy, the sweet spots in the balance between accuracy and computational cost. And SAPT-DFT is pretty powerful out there as well, so that's often the method of choice, because it can be nearly as accurate as the best wave function based SAPT, and it's much cheaper, so it can attack bigger systems. All right, so that's the bread and butter of SAPT calculations. So probably many of you will run some of these calculations. I wanted to mention, so we can do all of that for interactions between closed shell molecules. I wanted to briefly mention what can we do at present between open shell molecules, but there'll be a talk by Michał Chapka later today addressing some specific aspect of that. So there's several open shell SAPT variants right there under development. So originally the first one comes from our dear FIMOL director, Piotr Żuchowski, where the first one was for high-spin open shell systems described by a restricted open shell determinant. So you can do SAPT based on ROHF. And I apologize for using the symbolic SAPT ROKS, because it's not SAPT-KS. It's a SAPT-DFT, the good one, on top of restricted open shell Concham. You can do the unrestricted variant as well. This comes from Michał Chapka and Piotr Żuchowski as well, a little later. Now, recently, again, thanks to Michał Chapka, Kasia Pernal, Michał Przybytek, you can do multi-configurational SAPT, and you can decompose and calculate interaction energy involving either generalized valence bonds or CAS-SCF wave functions, and it's more general to take a general multi-reference description of each molecule. So there's SAPT-MC, and now all of these approaches in principle are limited to the highest spin state of the complex. So if you want to have the spin splittings, you need to have a special approach, and there are lowest levels available for the so-called spin flip SAPT, which is the way to access the low spin states of the complex, which is actually, this development is a collaboration between Piotr Żuchowski and myself. So I'm throwing in this slide so that you have references later on. But how can we get these numbers? So what kind of software is out there? So I think there are 4 big codes that can run some kinds of SAPT, and then a few smaller ones that I'll also mention. And my favorite one is Psi4, because that's where I and my group are active contributors to Psi4. We're not the main players. This is a large collaboration, but definitely we enjoy being a part of this collaboration. In Psi4, if you develop and program a new method and your new code gets accepted into the official Psi4 release, you get a reward. You get a special Psi4 mug, a very nice coffee mug. So that's one of my, I think, the awards that I'm most proud of, my Psi4 mug. So, and for all of these programs, I wanted to list the capabilities, and the stuff in white is the bread and butter typical SAPT variants, and the stuff in yellow are the capabilities that are unique to a specific code. And I started with Psi4, and of course we will be using Psi4 today, and it has all of the standard SAPT, as you see. It doesn't have all of the OpenShell SAPT variants, but it has SAPT UHF. And it has some special things such as atomic and functional group SAPT and intramolecular SAPT that we will demonstrate later today. So let me postpone the specific explanation to once we get there in our calculations. It does have spin flip SAPT, and the exchange corrections can usually calculated in an approximate fashion. That's really good at the van der Waals minima, but can break down at short distances. But Psi4 can do better than this for several corrections. The first alternative is the code from Delaware and Warsaw, the SAPT code from Krzysztof Szalewicz. And well, in the old times, I contributed to that code as well. And it has all of the standard levels of both wave function-based SAPT and SAPT DFT. It has extensive OpenShell single reference capabilities, and it has its unique capability is the 3-body SAPT for non-additive interaction energies between 3 molecules at once. MolPro has a pretty nice SAPT DFT, and it has a few other capabilities, including SAPT CCSD, which is the intramolecular correlation from coupled cluster. Very accurate, very expensive, but useful for getting reference contributions. That's the work of Tatiana Corona. And I wrote it in yellow, but that's not the only code that has regularized SAPT DFT to estimate the charge delocalization term, but it's out there. And QChem, the unique capability is the so-called XSAPT method of John Herbert. He calls it extended SAPT. What it's extended by is effects of non-additive induction, especially. And it can treat 2, 3 arbitrary number of molecules. And non-additive induction, which is a big deal for molecular clusters, is taken into account. It can also calculate non-additive dispersion by means of MBD. So it incorporates MBD, and it has that part as well. Some smaller codes that I should also mention is GAMCore, so Michał Hapka, Kasia Pernal, the code for SAPT MC, CAMCASP, Alston, so SAPT DFT, and of course the regularized SAPT DFT is Alston's approach to isolate charge delocalization energy from the whole induction. And thanks Piotr for mentioning that PyBest, the Toruń package, also can run some sub-zero. So that's just for your reference. Today we will be exclusively using Psi4, and we took so I think before the break, let's start to make sure that we can get some practical calculations to run. So this is where we go. You all got an email from David about some new files that showed up on the FIMOL website that are appropriate for this workshop. So let me show you what's out there. So that's the FIMOL website. And if I go to the materials for the tutorial and SAPT tutorial, so first and foremost, there's this notebook called SAPT FIMOL Student. And there are 2 image files, 2 PNG files. So if you haven't done so, please download these onto your laptop, because we will be running this specific notebook, the SAPT FIMO student. That's out there on the FIMO website. Yeah, we didn't want to put it online too early so that you don't play with it beforehand, but it's out there. So if you haven't downloaded it, please go ahead and do so. And in the meantime, I'll do the next steps. So I have my Anaconda navigator here, which is the graphical user interface that I use to launch Jupyter notebooks. And we all created an environment for the for this specific workshop, and in the instructions we named the environment workshop. So that's what I have. I see that I have a whole bunch of different environments, and I want to use workshop. And I'm launching a Jupyter notebook, and this is where we will open in Jupyter from our browser the notebook for today. So if you don't use the GUI, if you use command line, you need to do two things. First, type conda activate workshop to make sure that you're in the right environment, and then you do Jupyter-notebook. And that should open a Jupyter notebook in your browser. So I'm switching to my browser here because I've opened this Jupyter notebook. And immediately, if you open the Jupyter notebook, it will show you the files in your current directory. So you have to navigate to whichever directory you put the notebook in. So for me, as you see, it's Teaching Psy for Education Instructor, Lab Symmetry-adapted Perturbation Theory, but you probably put it in a different place. And there's the SAPT FIMO student, and this is what you click to open your notebook. And if you opened your notebook, I'm trying to get to the tab right, or maybe I'll just open a new one. So I clicked the SAPT FIMO student, and the thing is I have it already open. So what if I close this one? Oh, now I can access that. So this is the notebook. So who's able to get this notebook in the web browser? Who's got it open?
So what was the command line?
First conda activate workshop, and then Jupyter-notebook together. And it will show you the directory listing, so you still need to find your notebook and click on it. So who needs more time right now to get it open? Okay. All right, so this is a notebook that I hope that, well, you have it available, and I hope that will be useful for you. It has blanks, so this is meant for the students, for you. So you will have to complete some code here or there to get things running. So there are some pieces there that are exercises for you, so that's very interactive. So I'm thinking of making sure that we are all on the same page, and then it's almost time for break so that we can do more interactive stuff after the break. So many of you know Jupyter notebooks. Who's new to Jupyter notebooks? That's absolutely okay. So yeah, I don't see any students being new to Jupyter notebooks. I see us older folks being new to Jupyter notebooks, so I think that's saying something. So that's very normal. So that's like an electronic lab notebook. And in principle, like in the simplest form here, it has two kinds of cells. So this is a cell, and this cell contains just some text in the format called Markdown, which is like a simplified HTML, where with the text I can do bold, italic, headings, citations, things like that. And the other kinds of cells are like this, and this cell contains a Python code. And to run a cell, and we will be running these cells from the top to bottom one by one. There are other possibilities, but we'll try to make sure that we do everything in order. To run the cell, I have two choices. I can click here, you see run in my menu, and I ran this cell. I'll tell you in a second how I know that I ran this cell. But the other choice, the keyboard shortcut is Control-Enter. I think it's Shift-Enter on Linux, if I remember correctly, but on a Mac and on Windows it's Control-Enter. So this number here in 2, when there's a number, it tells me that this cell has been completed. Before I ran anything, there was nothing in here, in. That's the cell that hasn't been run. With a number, that's a cell that has completed. If you see a star here, it means that this is a cell that's still running. And we won't run any huge stuff here, but there will be some cells that take up to, say, 30 seconds to complete. And I think there's one cell that is like a 10-minute cell, but so at the very end. But if it shows a star, then it means that it's still running. So there was no interesting code in that. As you see, that's just the basic information about this notebook, which is adapted from something that I wrote for the Psy4 Education project as a general introduction to weak interactions and SAPT. But I've added more stuff for FIMO, so it's not the same as the Psy4 Education lab, but there's some basic information about what's in there and the project, and there's an explanation. I won't read that, but you have the notebook, so I do encourage you to read through the explanations in these cells that give you both some background on theory and also more precise instructions on what we're doing. But I'm going to move on to the next code cell, and this is where we really prepare the ground for us running Psy4. And this is Python code, of course. And the nice thing about Psy4 that I really like is that I don't have to learn a special syntax for the input file. I've learned the Molpro syntax. I learned a bit of Gaussian syntax. Old Dalton, which was the worst, probably. New Dalton is much better.
I think the worst is the old SAPT with the name lists.
Yeah. That's definitely not my favorite either. But what I like about Psy4 is that I can just use regular Python code. Now you see that at one point I just do import Psy4. So Psy4 is a library from the Python point of view, just as many other libraries that you've probably seen that I'm importing here. So importing the NumPy, so the library for matrix operations, numerical Python, SciPy, scientific Python, and matplotlib for graphs. So just as I import these other very popular scientific Python libraries, I import Psy4. And that's all I need. Now I set a few options for Psy4. I set the memory, I set the output file, and I set for later on things like the basis sets and the basis set for density fitting. So I will run this cell. It will probably take about 2 seconds. So it's going. And it's done, and it just tells me that memory has been set. So if you run this cell and you don't get any output, no news is good news here. So if you get no output, but you have a number here, you succeeded. You imported Psy4. If you get errors, well, errors are not good news. So this means that something went bad. And I got the information of how much memory has been allocated. So can you raise a hand if you ran this cell and either got no output or the one like me?
Still have to find the run button.
It's possible that, so from the cell menu, yeah, Linux is Shift-Enter. For like if you have your cursor in the cell, you can run it with a Shift-Enter. For the Mac and Windows people, it's Control-Enter. So I think that's the great time for a 15-minute break. We all need coffee or water, and if anybody needs some last-minute help getting things to run, then I'm here. Don't close your notebook, but once again, if you run this cell and you got either no output or this memory set to something, you're good to go for the second part. All right, see you soon. Welcome to the second episode of the award-winning series SAPT. In the first episode, we ran all through the boring PowerPoint, and we finally got to do something. And we started running the notebook, and we imported Psi4. And note that, as usual in Python, all the instructions that start with Psi4 are, of course, calls to the Psi4 library. So we used it in particular to set options. As you see, we gave a lot of options to Psi4 at once. If you're intermediate or advanced Python user, you immediately recognize that what we passed on to set options is a dictionary. You see these curly brackets. And this dictionary can hold as many options as we like. And some options, as you see, have values that are strings, like this basis set, and some options have values that are real numbers, like the tolerance for integrals. So we told Psi4 how much memory to use. We told Psi4 what basis set to use. We didn't yet tell it what kind of calculation we want. And we didn't tell one important thing, what molecule or what complex we want. So we will need the geometry specification soon, and Psi4 will accept Z matrices, Cartesian coordinates, you name it. So either one will work, and we'll use them interchangeably. And for our first practical example, I wanted to select something small. So we will calculate the potential energy curve of interaction between two helium atoms. So that's a very simple system, complex bound by dispersion. And potential energy curve means that we will change the distance between the two atoms. And of course, the interaction energy changes as a function of this distance. And at first, we will use the supermolecular method. So we will calculate this interaction energy as a difference between the total energy of two helium atoms and the energy of the sum of the energies of individual non-interacting atoms. And we're gonna run, I think, 11 distances. So I'm creating a list of distances. And I will calculate CCSD parenthesis T for every point for this helium dimer. And of course, I will calculate Hartree-Fock along the way. And I'm just running this cell, which is super fast because that's just declaring a few things. That's the first cell under the one that we ran before. So we have imported Psi4. So these distances are in Bohr, and I will calculate the interaction energy between two helium atoms for 11 distances. So I just prepared some NumPy arrays full of zeros for just the place where I will hold the results. And as you see, these two arrays are 11 by 3. Why by 3? Because I want, at least temporarily, to have 3 numbers for every distance, EAB, EA, and EB. Before I subtract, I have to run a bunch of calculations. So this is where we'll actually get, in this loop, in this next cell, we will get the coupled cluster numbers. So as you see, there's a for loop where we will run over all of these distances, 11 distances. And here, this is where we have to define the geometry. So we will define this geometry by using Psi4.geometry and passing a long multi-line string. So these triple quotes denote a multi-line string that continues until you find another set of triple quotes. Everything in between is this string variable, which has the geometry. So I have 2 helium atoms, so I put the first one at 0, 0, 0, and the second one at 0, 0, and whatever the distance is. So that's where I take the number of distance and convert it to string. Now, when we run 2 molecules, such as in SAPT, we use these 2 dashes to separate the first molecule from the second, so that Psi4 knows that everything above those dashes is molecule A, everything below it is molecule B. And now the energy calculation is as simple as this. So this is, I just call psi4 energy, and I'm telling psi4 that I want CCSD parenthesis T. And once, as this if you want, you can start this cell. It will run for maybe 15 seconds. And once this energy calculation is completed, I save the numbers for both the Hartree-Fock energy and the coupled cluster energy into these NumPy arrays that I created before. So the syntax is psi4.variable. That's a way I can access any variable, any named variable that psi4 has generated for me before. And when psi4 performed the CCSD parenthesis T calculation, it saved the result in atomic units in the variable CCSD parenthesis T total energy. The variables have a name. But of course, if I did CCSD parenthesis T, it means that I did Hartree-Fock along the way, and I actually even did MP2 along the way. So I can access these partial results with properly named variables as well. So this first part of the code that I highlighted here takes care of the coupled cluster calculation for the dimer AB. But now I need to subtract the energy of A and the energy of B. I know that these are two identical helium atoms, so I should subtract twice the energy of an atom. I wasn't that smart, so I did the calculation separately for each atom. And the difference is really how I specify the geometry. So instead of placing two helium atoms, I have one helium atom, and then a helium ghost atom. A ghost atom is a place where there's no nucleus, no electrons, but there are basis functions. So I do want the basis functions in place of the other molecule to avoid the so-called basis set superposition error. So for those of you who know, what we're doing is a counterpoise corrected calculation where all the pieces are in the same basis set of the full complex. So this is where I calculate the energy of molecule atom A alone, and I save it into these variables, and then I do the same for molecule B. So I will run this cell. It doesn't produce any output. It just runs all the calculations. So if it doesn't generate, once again, no news is good news. If it doesn't generate any error but just completes, then it means that we have prepared these whole arrays of coupled cluster energies for 11 data points. Now, all the calculations take longer if you're also doing WebEx, so, but here we are. So as you see, it's completed. After all, it's a small system. So we want to display these values, so we want to make a graph of both CCSD parenthesis T interaction energy and Hartree-Fock interaction energy as a function of distance. So this matplotlib code, we imported matplotlib as PLT. So we'll generate a graph, but we need to create the set of numbers with the interaction energies for Hartree-Fock and CCSD parenthesis T. So as you see, this, I gave you an incomplete notebook, and whenever it says complete something, it means that the code will not run like this. We need to fill in the blanks. So how will we calculate the Hartree-Fock interaction energy based on the numbers that we have? So note that we saved for every geometry I, we saved the value of the AB, Hartree-Fock energy, as EHF I0. So I'm doing a copy and paste, and I want to do it for all of them. So this NumPy syntax tells me that I'm taking the entire row of this array and just the column number 0. So that's the set of all AB energies, and I need to make a subtraction. I need to subtract A, and I need to subtract B. So because I'm dealing with NumPy arrays, if I do that, I will get I perform all the 11 subtractions at once, and I'll get an array of interaction energies. So for every row, I subtract the first and the columns number 1 and 2 from the column number 0. So I subtract EA and EB from EAB. Now all of these numbers were in atomic units, and I want it in kilocalories per mole. I think it's a more common energy units. So correct me if I think that's a reasonable conversion factor from. Maybe I'll use my quickly 627,509, 627. See? I should be remembering that. That's a better conversion factor to kcal per mole. And now by copy and paste and change, I'm going to do the same thing for CCSDT interaction energy, and I saved these numbers under the name ECCSDT. So I need to access ECCSDT every row, column 0, to get the AB energies. I will do the same for A and the same for B. So I filled in these two lines. As you see, this is how I make the subtraction of NumPy arrays to get the interaction energies. So the 0 column was AB, the first column was A, the second column was B. I make the subtraction and convert the numbers from atomic units, so from Hartree to kilocalories per mole by multiplying by this conversion factor. So I'm ready to run this cell. All right, who's got a graph when you run this cell? Okay, great, we have. You did? Okay, great. So because this is a graph in Jupyter Notebook, so it's actually dynamic, you can zoom in. So I'm going to go ahead and select the zoom option and just select a rectangular area to zoom in on. So what we plotted are two curves. So what changes here is the distance between two helium atoms. And we have the coupled cluster interaction energy as blue circles, and the Hartree-Fock interaction energy as red crosses. So what did we find out about these two helium atoms? Are they held together? Is there anything holding them together? Dispersion interactions. So I'm glad that we don't yet know that, we haven't yet proven that, but we will. But the coupled cluster results definitely show attraction. So they show negative energy. So the energy of two atoms together is lower than if they were apart. So there has to be some attraction, and exactly it is due to dispersion interaction. Now, I guess another hint that is due to dispersion is that if you do Hartree-Fock, which has no electron correlation, so no dispersion, you get no attraction. So we all learned in freshman chemistry that there's no such thing as helium-2 molecule, because you have to put 2 electrons on a bonding orbital and 2 electrons on the anti-bonding orbital. So this picture of filling in the orbitals is the Hartree-Fock picture. So as you see, Hartree-Fock predicts that there is absolutely no bonding between two helium atoms, and a more accurate correlated method, CCSD parenthesis D, tells us, wait a minute, there's dispersion forces, and this is what provides the attraction. But to know for sure, we probably need to run some SAPT. Later on, there are some questions for you here that you might want to try to answer to check your understanding. But here we move into SAPT, and we will be running SAPT 0 in here. So that's the formula for SAPT 0 that we've already used. Now, note that for coupled cluster, I needed to run 3 calculations, AB, A, and B. For any kind of SAPT, I run 1 calculation only, because SAPT is directly aimed at interaction energy. I don't have to do any subtractions. So this cell runs 1 calculation for each distance. And the key point is, of course, psi4.energy at SAPT 0. Energy SAPT 0. So this is when I'm telling psi4 to calculate the SAPT 0 interaction energy for these two helium atoms. As you see, it's again in a loop over distances. So I will calculate this interaction energy for every distance. And this calculation remembers all the different SAPT pieces and stores them in variables. So I can access SAPT electrostatics, exchange, induction, dispersion, SAPT total energies. All of them were calculated at once, and I'm just converting them to kcal per mole. So in this loop over the distances, I will run a bunch of sub-zero calculations and store the results in these arrays. And finally, I will make a graph in matplotlib of all of these SAPT energy components. So at this point, if you run this cell, which again, it was a short calculation, as you see, we obtained a graph that shows us how the four main parts of SAPT, as well as the total SAPT interaction energy, change with the distance. So the total SAPT zero interaction energy is the black curve. And as you see, we get some attraction in here. And probably it's a good idea to zoom in as well. Now, matplotlib is smart enough to know that if I want a smaller part of the graph, I still want my legend in there. So don't worry, we still have it. So now, looking at these terms in the interaction energy, in sub-zero interaction energy, tell me, where does this attraction come from? So there is attraction between two helium atoms, as indicated by the total interaction energy, the black curve. Where does this attraction come from? And we already heard dispersion, and now we have a proof. You see, that's the dispersion alone. And for the large distances, the entire attraction is coming from dispersion. Now, exchange provides repulsion. Exchange is the reason why these two helium atoms were not going to fall on top of one another. And electrostatics is the red one, induction is a green one, so they are weakly attractive here, but they are much less attractive than dispersion. And moreover, they disappear at intermediate distances where all of the long-range attraction for two helium atoms is due to dispersion. Of course, the reason is because that these are atoms, so they don't have any dipole moment or any higher multiple moment, so they cannot have any long-range electrostatics or induction. So it would be actually nice to see what's going on if we have some long-range electrostatics or induction. So the next thing we're going to do is go from the helium to helium atoms to two other molecules. So the calculations will be a tiny bit longer, but we still can accomplish that. But maybe before, I wanted to take a look at one thing. So what do we know about the long-range behavior of dispersion energy? Well, it goes to 0 when R goes to infinity. What is the rate of decay of dispersion? How does it go to 0? We've all seen the London form. Go ahead. It's not exponential, it's slower, actually. So the exponential is the way these blue and green and red curves go to 0. The magenta one got slower, and I know I'm ignoring retardation, so I will say that it goes to 0 as the inverse 6th power of the distance, 1 over r to the 6th. Do we see it in our data? So I will use SciPy curve fit to fit a function of the form a constant a times r to the negative power negative n to see what exponent corresponds to the long-range behavior of my dispersion energy. So the SciPy optimized curve fit can fit parameters to some function, but I need to define this function. And the function depends on x and the two parameters, param1, param2. I hope I'm doing it right. And I want to fit the function, so I'll return the value that is a times r to the negative b for parameters a, b. And what I'm really interested in is this parameter b. So what's the optimal inverse power of the distance for the decay of this function? So I want to program a times r to negative b. So a is param1. And now I need the power, so I'll use numpy power. And I will raise x, so r to the power negative param2. And I hope I did it right. If I missed something, I will, first of all, I have my secret copy where I cheated and solved everything ahead of time, but let's try. And now please note that I'm using SciPy optimized curve fit to fit the parameters in this functional form, so function f. But the data to which I fit are a few of the distances and dispersion energies. But the Python experts, please tell me, what does it -5 mean here? Go ahead.
Taking the last, you're beginning at the 5th position, but starting from the end.
Yes, so I'm taking the last 5. So from the 5th from the right all the way to the end. Why did I do that? Remember that my distances are from the smallest to the largest, so I'm only picking the 5 largest distances, so probably from here on. The reason is because I want to pick the asymptotic behavior. So short range values have nothing to do with my asymptotic, so I need to fit the proper power to the long range data. So let's run this cell. Okay, I messed it up badly, I admit, so I don't want to take too much of your time, so let me param 2 times. Okay, I know what I did. That's kind of funny. So I'm returning the optimal dispersion exponent, and I'm referring to the first parameter. But first parameter is this one. But I'm interested in the exponent and not in the constant. So I'm just switching places, param 2 and param 1, because I'm interested in the first parameter, which is the optimal exponent. All right, that's much better. So we're pretty close to 6. So what we found out that if I fit an inverse power function to these 5 longest range dispersion energies, the best way to describe them is by r times r to the power -6.3. That's pretty close to 6. I would even state that it makes sense that it's bigger than 6 because there are further terms in the asymptotic expansion of dispersion energy. So there's C8 over r to the 8 and so on. So we see some remnants of that in the form of a power that's slightly larger than 6. But that's pretty close to 6, so I think we're getting the right physics. All right, so let's do kind of the same for water. So this is a slightly bigger molecule, of course. We'll do 10 distances. We don't want to wait too long, so we'll decrease the basis set to AUG, CC, PVDZ by using this new Psi4 set options. So whenever I add another set options, these options add or replace the previous ones. So don't be worried that I only specified this option. I haven't forgotten all of the previous ones. So now I'll specify the water molecule in a form of a Z matrix. So that's my first water molecule with bond length 0.96 and bond angle 104.5. I think that's close enough. And now I'm placing the second oxygen at a specific distance from the first one. So I will change the distance between 2 oxygen atoms. I'm not like a geometry guru to define quickly the distance between centers of mass, so let's keep it simple. So the OO distance will be changed. And here the way I put these 2 water molecules is in a hydrogen bonded configuration, so that one of the water molecules is the hydrogen bond donor, supplies this H interacting with O, and the other one is the hydrogen bond acceptor. The second one is actually an acceptor. You note the X in there in the Z matrix is just the dummy atom. It was easier to first specify the dummy atom halfway between these hydrogens and then do the hydrogen. So now units I can always specify in my geometry if I use Bohr or Angstrom. And this way I define the Z matrix. And now I need to run coupled cluster for this calculation, and I also, for this geometry, I need to run coupled cluster for molecule A alone and molecule B alone. So I'm going to go back to one of my previous cells where I had coupled cluster calculations and do some copy-paste to fill this field quickly. So that was how I did my coupled cluster calculation, and I want to do it again. So Now, what do I need to change besides the indentation? So right now, my variables, the arrays where I store the numbers have the H2O part of the name, just because I don't want to forget my helium dimer values when I do the water calculation. And I will also save the MP2 energy for later. That since I'm running coupled cluster, it might be a good idea to have MP2 as well. And of course, it's not really possible to run CCSD parenthesis T without getting MP2 along the way, so I can access MP2 total energy. So what have I accomplished if I run this part? I will have run the coupled cluster calculation for 2 other molecules. What else do I need for the interaction energy? I need to run similar coupled cluster calculations for 1 water molecule at a time. So how do I do that? I copy and I paste. So that was the code for the dimer. So let me remove this. So the pasted code starts here, so it's not the dimer, it will be monomer. Sorry, press the wrong thing. Monomer A. And I run coupled cluster, and because that's monomer, so I save the values in the second column of my data. And I need to do the same thing for monomer B. If you think I'm doing something wrong, you are absolutely correct, and you will tell me in a second what am I doing wrong. But first, let me copy and paste this once again and call it monomer B, and save the numbers in the third column of the array. So what am I doing wrong? I wanted to calculate 2 water molecules and subtract the energy of the first water molecule and then the energy of the second water molecule. But so far, I'm running the same 2 water molecules 3 times. Right? I need ghost atoms, yes, so because I need 1 molecule at a time. So here is my monomer A, so I need to make sure that monomer B is made entirely out of ghost atoms. So all the 3 atoms, remember that's a water molecule, so there's 1 oxygen, 2 hydrogen, are ghost. So now they are, and for monomer B, the first water molecule needs to be ghosts. So once we have that, I think we're good to go. We have all of that in the loop. I will start running this cell, so it's running. And because these are coupled cluster calculations on a laptop for a slightly bigger molecule, maybe a good idea for me that I forgot was to add up a printout after every calculation to tell you how far along we are. So that in hindsight was certainly a good idea, but I'm already running this thing. So
could you scroll back up in the entries a little bit? Yeah, that's good. I'm still back there.
All right. So that's so once it's running, so we're getting the set of coupled cluster interaction energies between 2 waters. We'll save the numbers into these 3 arrays. So right after we can do the subtraction, and we will make a graph. Now, did I remember to make the subtraction? I forgot to make the subtraction, so I will have to rerun this cell anyway. So then I can add some printout, but I'll just copy and paste the subtraction. So just like before, I'm using this syntax to you outside the loop. You see there's no indentation, so I'm doing this when my loop is done. I take the AB value minus A value minus B value times the conversion factor to save the array of interaction energies, and I promise to add a printout after each point. So point is number I. So here's the end of my loop. So I will add a print in the loop. Completed. Point number. I prefer I plus 1 because I starts from 0. So now I'll rerun it because I started running it too early. And now at least before I'm done, I should get some partial printouts. And at the very end, after I make the subtraction, I will make a graph again. And I will show this interaction energy for Hartree-Fock, MP2, and coupled cluster between the two water molecules as potential energy curves. I know it's doing the right thing. Yeah, we did the helium dimer first just because we knew that it's the fastest calculation of all. Here we are using ADZ, so it's not a huge calculation. And as I mentioned, I observed that before that things go slower if you do Zoom or WebEx with your laptop, but I think we should have the first one done soon. So once again, I think it's good time to see what we did. So we are calculating these coupled cluster interaction energies between two water molecules for different separations. So we define the geometry with a Z matrix, where we shift the other water molecule at a specific OO distance from the first one. And because this is a supermolecular calculation, I need to perform 3 coupled cluster total energy calculations for every point. First for the entire system AB, then for molecule A only with the atoms of B replaced by ghosts, just like in here, and then molecule B only with the atoms replaced. Ooh, that's worse than I expected. We could decrease the basis set, but actually I think it's important for us to power through this calculation. Somehow without Zoom or WebEx, I think I need about 20 seconds per each. Oh, something? Oh, probably what I didn't. The problem was that I was running it once and then I didn't properly stop that unsuccessful one. So now we're running it properly. I apologize for this, and now we got everything shifted away from the screen, so this is now much better. So this dimer calculation, AB calculation, will save us the first column of these 3 arrays with the Hartree-Fock total energies, MP2 and coupled cluster. Then we will run the ghosts on the second one and save the energies in the second column. Then we'll run the molecule B with ghosts in the place of first one. It shifts horizontally too easy now because there was some long line, I think. Oh, it completed 2 points by now, so we have progress. And finally, once the 10 points are completed, we will find out the interaction energies with a subtraction of the monomers A and B from the AB value converted to kilocalories per mole. I will print these arrays, which are just sets of numbers, so that we can take a look at the numbers in kilocalories per mole, but I'll also make a matplotlib graph plotting the Hartree-Fock MP2 and coupled cluster interaction energy between two water molecules. So we will see a graph soon, and as the numbers are crunching, so what do we expect on this graph? So we got two different curves for the helium dimer. One of them was purely repulsive, and one of them had attraction. So what do we expect this time? Will we get attraction or maybe repulsion? I oriented my two water molecules like that.
Could I ask you to scroll back to monomer A?
Yes, absolutely. We are halfway done, by the way. We completed point number 5. This is monomer A. And like first we define the geometry and then we perform the calculation. So everything that I highlighted is monomer A. So will we get attraction or repulsion? At short range we get repulsion. That we know that already. And say at intermediate distance? Well, we know hydrogen bonding is pretty powerful and very important for properties of liquid solutions and liquid water. And hydrogen bonding is definitely an attractive interaction between two water molecules. And I oriented my water molecules so that a hydrogen bond can be formed. So I do expect some attraction. Now, definitely out of the 3 results that I'm plotting, I will trust my CCSD parenthesis T data most. I wouldn't call it a gold standard because I lowered the basis set, but what I'm doing, in fact, I think I could call it a silver standard of interaction energy. Now, MP2, I will trust a little less than coupled cluster, and I will trust Hartree-Fock the least. Now, if I go to large distances and do the same fitting as before, what kind of inverse powers of distance would I expect? If I do dispersion, I will still get something close to r to the -6th. And of course, before I can do dispersion or do electrostatics, I think I need to run SAPT. I will run SAPT next. But I'm almost there. We're on the last point, so, and since SAPT is sub-0, it's going to be faster than this. And since I need to, okay, great. So I got 3 curves. They are all attractive. One of them is significantly less attractive, and that's Hartree-Fock. And then MP2 and coupled cluster are almost on top of each other. So MP2 performs really well for these 2 water molecules. It's not always the case for any system. If I replace 2 waters by 2 benzenes, my MP2 would have been pretty terrible. But for 2 waters, it works well. So, but Hartree-Fock, of course, works worse because it doesn't have dispersion, first and foremost. But this time, Hartree-Fock was repulsive between 2 helium atoms. And now we get attraction. What kind of an attraction can it be? So the red curve doesn't have any dispersion. So why are we getting attraction there? Electrostatics. There's definitely something that if the molecules were further apart, I would call a dipole-dipole interaction, a favorable one. Because they're close enough for the densities to overlap, I won't use the long-range names, but there's definitely favorable electrostatics. So let's run some SAPT, and I guess I need to copy and paste the code to run SAPT, and I'm gonna cheat and copy and paste from a complete notebook. I'm missing the line, the for loop. So I will loop over the distances for water, and as you see, run SAPT 0 for each distance and save these 5 numbers, the electrostatics, exchange, induction, dispersion, as well as total energy. That's a faster calculation, but I did something wrong, and that's kind of interesting. Division by 0, so
You need to change geometry every step.
fantastic, absolutely. That's how, that was a really bad idea on me, right? See, these things are always harder to do when you're out there at the podium. So now I need to fix my indentation before Python complains, and I copied and pasted the same geometry code as before. For a SAPT calculation, I need to separate the first molecule from the second one, so these 2 dashes are obligatory, and I'm changing the distance. And this time, as you see, we're using a Z matrix, and that's fine. Okay, so that's actually I might need to. That happens if you run things out of order in a Jupyter notebook sometimes. So I know if I ran everything from the start, that would fix it. So I won't run everything from the start, but I'll import Psi4. You don't have to do that, but I'll import Psi4 from. So if I go to cell, I can always clear the outputs. I didn't press it. All outputs clear. So it's telling me that I haven't run anything. And I'll just quickly import Psi4, because if I don't import Psi4, nothing will happen. And again, you don't need to do that, but I will need to make sure that I run this in ADZ and not in ATZ. So I'll just copy and paste it here, which you don't need to do that. I'm only doing it because I don't want to run the previous cell again. And now it's running. It won't take as long as the previous one. So this is 10 SAPT 0 calculations, and I will remember the components, electrostatics, exchange, induction, dispersion, as well as total energy in these arrays, so that I can make a graph of the same kind as I made before for the helium dimer. So we know that we got attraction from every approach, even Hartree-Fock, even though there was no dispersion. We got less attraction for Hartree-Fock, but we got attraction. And somebody said correctly that this attraction is due to electrostatic energy. So I'm expecting more, bigger component of electrostatic energy in the overall interaction, and it's probably going to be a large term. Large attractive term. I still expect that there will be dispersion energy. I don't necessarily know what to expect about induction energy, but I know that overall the induction energy is an attractive component, and the exchange energy will definitely provide some short-range repulsion.
Connor, could I ask a question?
Go ahead.
How is hydrogen bonding reflected in the results?
So hydrogen bonding, according to SAPT, is multifactorial. So the binding is primarily electrostatics, but absolutely not exclusively electrostatics. So it's a big oversimplification if you say that the hydrogen bonding is due to like dipole-dipole forces, because there's a large component of electrostatic energy, but there's everything else as well. And dispersion, as we'll see, will contribute about 1/3 of the binding energy between two other molecules.
I could just add to that. I mean, I would say that both the dispersion and induction contribute quite substantially. And in the induction, there's a substantial contribution of both classical polarization and charge transfer. So it's all of these. And if you use just the electrostatics, you actually miss out on the bulk of the effect in hydrogen bonding. But still, chemistry textbooks treat it as an electrostatic interaction, but it isn't.
So if I remember correctly, and there's actually some cells in the notebook later that calculate these numbers, the electrostatics provides about 140% of binding at the minimum. So it's like gives more attraction, but of course there's first order exchange that cancels a lot of that. So the net effect is much smaller. And then induction and dispersion each are responsible for about 30% of binding. So that's the net effect is that you cannot ignore any of these. So hydrogen bonding is quite, I wonder why did I run something? I did expect to have results by now, so I'm just seeing if I've done something stupid, and I don't think I have. So I'll give it a bit more time before trying to, I remember that we have this output.dat file that we're creating as the output from the actual Psi4 calculation. So we don't see the whole raw output file in the notebook, and I think it's good because that would be too much information, but it doesn't mean that it's gone. So we kind of hide the usual information from the quantum chemistry code. We don't go through a raw output in the notebook, but if we want to access it, it's out there. So I guess I'll open a terminal and see what's going on with my output.dat. And I think there is some danger that I missed something that I don't quite understand. So what I'm going to do is really restart it the proper way. So I'll restart the kernel and clear all output. And as we're talking, I'll fill in the cells as they go. So I think it's good to be able to have this. And in general, that's actually the problem with Jupyter notebooks, that things get crazy if you start running cells out of order, because various variables can be, internal variables of Psi4, for example, can be changed throughout, and then if you run something in the wrong order, you're not getting the right thing. So I apologize for this. I will quickly rerun the coupled cluster. Now I don't want to reset these variables, and we'll get all of these graphs again. Like similar to the hydrogen bonding, a very interesting topic is the sub-description of halogen bonding. And there's a beautiful paper by Anthony Stone with SAPT and trying to understand what's going on and why, in particular, we get the bonding in a very specific distance. After all, we need to have the electronegative atom approach the halogen from exactly the opposite of the covalent bond. And the important reason is actually exchange energy. I know the exchange energy is not something that holds things together, quite the opposite. The exchange energy is a repulsive force, but there's a lower repulsion in this specific direction, and that's how we get halogen bonding as a directional force. So I'm just redoing coupled cluster. I guess that's bad planning for my part, but how are your laptops doing with, so you, of course, you don't need to redo anything. So does anybody have a SAPT picture? And before we all see the SAPT picture on the projector, can you tell us how your SAPT picture looks? Go ahead.
There is attractive electrostatic energy. It's
Mhm.
dominant attractive term. Right? We have then induction and dispersion being attractive at short range, and of course all of the exchange part goes up. It's repulsive, and there is a minimum in the total sub-zero curve.
So we picked the, thank you, Michał, we picked the orientation right. We picked the orientation that passes at least very close to the global minimum. So we will get the attraction, just like we got the attraction from coupled cluster MP2, or even Hartree-Fock. And exactly as Michał said, the biggest part of this attraction comes from the electrostatics energy, which, as we will see soon, was large and negative. But neither induction nor dispersion energy can be ignored, their negative contribution. And just out of curiosity, who else is able to follow all the cells in the notebook? Excellent. Yeah. Great. Yeah, I'm glad that you didn't mess it up the way I did. To make sure that everybody sees the graph, I still want to use these couple minutes when we're 60% through the 70% through coupled clusters. So then SAPT is faster if you actually run it and not do whatever it was doing. So going further, so I want to run these further cells yet, but I think it's useful to take a look at this geometry. This specific geometry is the first point on our potential energy curve. So that's the XYZ coordinates of OH, H, OH, and H. And it would be nice to maybe write a simple code to check the bond distances and bond angles, because I noticed when looking at my numbers that the energies of these two other molecules are different. Remember, these are the energies that I subtract when I perform a supermolecular calculation. And I thought maybe I'm doing too much work to calculate each molecule separately. After all, they have the same structure. But I looked at the numbers, and we'll look at the numbers that I got different energies for the two molecules. So maybe it's good to understand what's going on. So if you're already there, I encourage you to try to write some simple code to, okay, that's my coupled cluster, that's my MP2. Let's run my SAPT 0 now properly, to maybe write some code to calculate the bond lengths and the bond angles in each water molecule. Okay, see, once I did it properly, that was a fast calculation, and I know that we already knew from Michał what's going on, but that's exactly what we expected. So this red electrostatic energy is the biggest attractive contribution. That here, the second point is actually the van der Waals minimum. That's the lowest energy on the total curve. That was also the van der Waals minimum for coupled cluster. And then there is induction, that's the green one, and there's dispersion, the magenta one. So both of these are attractive, but less attractive than electrostatics. So this cell is just defining some variables, and I will use some code by copy and paste to find the distances and find the angles. So there's, of course, many ways to do that, but NumPy can calculate dot products, and it can calculate then the dot product can calculate vector lengths, and using a dot product and the product of the lengths of two vectors, I can get the cosine of the angle between the two vectors. So this code, sorry I went quickly with copying and pasting. You can either think about it as a simple exercise to write the code for the distance and the angle, or I'll provide this code. And let's run it. That's really quick because that tells us something interesting. So this cell printed out the 4 OH distances and the 2 HOH angles and the MP2 energy of each molecule. Are these two other molecules identical? Well, they have identical geometries. I'm using the same bond lengths, the same bond angles. And I hope you still remember that these were the values that I put into my Z matrix. So I think that's reassuring that I haven't messed up my Z matrix, because I could totally do that. But still, somehow, if I look at all the digits, my energies of the two water molecules are different. So what's going on? Why does one of these water molecules have a different energy than the other? Go ahead.
Because they're polarizing each other in different ways.
They are polarizing each other in different ways, which we will see both in the supermolecular method and in the SAPT calculation. But these two calculations had one water molecule at a time. The other water molecule was not there, so there was nothing to polarize. So the reason is different. Yes, Johannes?
There are still the ghost atoms from the other molecule.
There are ghost atoms from the other molecule, and they are differently located. So the molecule A sees the ghost atoms in the place of molecule B, which is a different location from the point of view of molecule A than for B. So the different location of ghost basis functions is exactly the reason why these two MP2 energies are different. So when you calculate some interaction energies from a supermolecular method, make sure before you decide, oh, it's twice the same molecule, I can calculate one of them and subtract twice. Make sure that you really can. So remember how for the helium atom we found the optimal inverse power of distance for dispersion energy. Now I want to do the same thing for dispersion, electrostatics, and induction. So I'm just going back to see what kind of code I need to copy. And I can use the same function f that I already defined, but I definitely have to use the distances for water and dispersion energies for water. And I'll call it ndisp underscore H2O. That will be the optimal exponent, optimal dispersion exponent for water. And I wanted to do the same thing for electrostatics and induction. So I'll copy paste this line twice and make changes. So first elst, so I'm fitting, I think I called it elst, but I'll double check. And this is end, and I'm fitting end. So before I run it, I'll first check if my variable names are right. This is where I created them, and yes, this is how I called them. I somehow remembered. And now we use the same curve fit to the same function, so A times R to negative B, to find the optimal power corresponding to electrostatics, induction, and dispersion separately. And I always, just like before, I use the 5 largest distances only and the energies for 5 largest distances to make sure that I fit these exponents to the asymptotic data and not to the short-range data. So what did we get? The optimal dispersion exponent, 6.55. That's still pretty close to 6, and it's still over 6. So I think we're good. Induction, 7. Like on theoretical grounds, I would expect similar to dispersion, so 6, then a bit over 6. Induction is smaller than dispersion, so slightly. So I guess 7 is acceptable. But what do you think about this optimal electrostatics exponent? Is this something that you expected or not? So if the molecules are far apart, which is what I'm interested in right now, this interaction is dominated by the dipole-dipole interaction. So a dipole-dipole interaction energy vanishes as an inverse third power of the distance. So I expect something like 3 and probably again a bit more than 3 because of the further terms. So that's actually pretty good. And you can see that the electrostatic energy extends to much larger distances than induction and dispersion just because this is the roughly r to the negative third decay behavior, and induction and dispersion have more like r to the negative 6. So if we actually fit the optimal exponents to the data, this is what we're getting. So I told you how we explain the long-range interaction energy between 2 other molecules by the dipole-dipole interaction. But what does it mean that we do it at long range? And what happens at short range? Is this dipole-dipole interaction of any use to describe 2 water molecules at shorter distances? Well, let's find out. So we'll write a code to be able to compare the SAPT electrostatic energy with the dipole-dipole interaction. But to find the dipole-dipole interaction, probably the first preliminary step will be to calculate the dipole moments of the 2 molecules, because I calculated a bunch of energies, but I haven't done any dipole moments. So right now I actually define the XYZ geometries of the separate water molecules. So I didn't like extract it from the Z matrix in any fancy way. I hard-coded that to keep it simple. And please note, I think this is the most interesting part of the code, where I'm calling psi4.energy again. I'm doing Hartree-Fock, but I'm adding this additional option, return wave function equals true, which means that I'm not interested in the energy, but I want to have the wave function back to play with it. And using the, and actually here I won't play with the wave function, but when I did that, I have also calculated the dipole moment along the way. And this psi4 variable SCF dipole is actually a dipole moment is a vector. So this is an array of 3 numbers. I get the whole dipole moment vector in this one array. So that's the dipole moment. As you see at the Hartree-Fock level, I keep it simple for molecule A. And I'm doing the same thing from molecule B. And I also calculate where the centers of masses are. So I have the coordinates of the center of mass of AB, dipole moments, and I wanted that to be able to compare the electrostatic energy to the dipole-dipole energy. And that's the formula for the dipole interaction energy between 2 dipoles. So it has this term with the dot product between 2 dipole moments over r to the third, and it has a term where you multiply, take a dot product of a dipole moment by the vector r. And the vector r here goes from the center of mass of one water molecule to the other. So I have some code to keep track of when I go from one point to another, how the center of mass vector changes. So I just need to copy and paste the code for the dipole-dipole interaction energy, where everything is already in atomic units. So I don't need to do any unit conversion. And before I run it, I'll explain exactly what we're doing. So I want to calculate the dipole-dipole term for all of the distances that we had. So looking at the formula for the dipole-dipole energy, I already calculated mu A and mu B, but I need to keep track of r for for the different distances, and r is the vector from one center of mass to the other. And to get this vector from one center of mass to the other, I have the the unit vector in the direction where I shift the second molecule relative to the other here, and I set the value of r as the original center of mass distance plus the shift, the length of the shift times the direction of the shift. So this code is designed to make sure that for every point on my potential energy curve, I have the right vector r between one center of mass and the second. And now I just wrote the function dipole-dipole, and I call repeatedly with different vectors r, dipole A, dipole B. So the first term is the dot product, where I'm using with numpy, the dot product between the first and second dipole moment, divided by the length of the vector r to the third power. And then I subtract 3 times dot product of the dipole moment of A times r times dot product of dipole moment B times r divided by r to the fifth, exactly as this formula says. So I program this dipole-dipole, and I will calculate it for the same distances of water. I'm making this array E dip for the dipole-dipole interaction energies. Why do I do that? Because I want to compare it to the overall electrostatics energy. So the graph I'm making right now will show the electrostatics energy from SAPT and this dipole-dipole interaction energy that I just calculated. So let's do that. All right. And I think it will be educational to zoom it in a little bit better. So at the long range, these two curves, the red one from the actual SAPT calculation and the blue one from the dipole-dipole, they coincide. They have the same behavior. So that the dipole-dipole interaction explains the long-range behavior of the SAPT electrostatic energy for these two orders. But at the short range, these two are dramatically different. So, and which one is right at the short range? Red or blue? Which one is meaningful? Which one is, so at the short range, they're very different. Which one is meaningful and which one is not? Go ahead.
Like charge penetration.
You have charge penetration.
Very short distance.
Yes. So whenever the densities overlap, it doesn't have to be a very short distance. At every van der Waals minimum, you have charge penetration. So under these circumstances, the multiple expansion doesn't converge, and it's not useful. So the blue numbers don't make sense at short range. And the red ones are the actual SAPT electrostatics with all the charge penetration effects included. So as you see, we get the kind of long-range behavior that we expected. But at the short range, the SAPT is actually quite different from the dipole-dipole term, and the SAPT is right, dipole-dipole term is wrong. Go ahead, Kathy.
Can you look at the dipole-quadrupole interactions as well and see how much of the difference between the SAPT and the dipole-dipole is due to the charge interpenetration versus higher multiple terms?
That's absolutely doable. Psi4 can calculate the quadruple moment for you. I haven't done that personally, but we have the capability to make this comparison. Absolutely, that would be the next correction that I'm sure will help somewhere out here in the intermediate range. It won't help really much around the van der Waals minimum. Okay, I believe the overall plan is to end at 12:15 around, so we have about 30 minutes, and there's a couple of things, directions in which we can go, but first, just to summarize this, we talked about the percentages of interaction energy from different parts of SAPT. So how we can use the SAPT analysis of interaction energy terms. See, I avoided using the word decomposition to see what really contributes to the binding. So let me copy and paste this code real quick to calculate the percentages. That's, of course, super simple code. So So I'm just comparing the total SAPT interaction energy, SAPT, water, and individual component. I'm multiplying by 100%. And I remembered that the van der Waals minimum is the second point of my curve. So the way I access the second point of my array is by giving it an index 1. So all of these ones means pick the second point on the curve that happened to be the van der Waals minimum. And as you see at the van der Waals minimum, electrostatics, induction, and dispersion contribute 141%, 33%, and 30% of interaction energy respectively, which is what we expected. Of course, they add up to much more than 100% because there's also exchange energy, first order exchange, that is repulsive and that cancels a lot of these effects. But definitely none of these terms are anywhere near negligible. If we want to understand the hydrogen bonding, we have to have all of these terms. So knowing the relative importance of induction, electrostatics, and dispersion in binding, I can actually do the kind of graph that I showed you in PowerPoint. I can place this water on a ternary diagram. So Psi4 has the code for ternary diagrams, and I don't think I need to fill in anything in here. So that's already. So this code is authored by Laurie Burns, and it's copied from the sources of Psi4. And what I did, I took everything I calculated today, so all the SAPT0 I calculated today, which means helium dimer and the water dimer, and looked at the relative importance of electrostatics, induction, and dispersion, and based on this relative importance, placed it on a ternary diagram. And I used blue for one of the systems and red for the other system. So we have 2 helium atoms and 2 water molecules. So which color did I use for 2 water molecules? So let's recall what was the biggest factor in the binding between 2 water molecules. The biggest one was electrostatics. So for the water molecules, we expect to be kind of close to the corner of the triangle with attractive electrostatics. So that's red. Red is water. Now, blue is helium. Now, for some large distances, we get like 0 induction and the numbers are so small that the ratios are not very accurate. So don't pay too much attention into these 3 points. But overall, the helium dimer is bound by dispersion. So it's all closer to this corner. So definitely if I want to, for example, benchmark a new DFT or a new machine learning approach based on a broad set of interaction energies, I don't think my 2 systems count as a broad set of interaction energies. I don't cover enough of the diagram already, but kind of like this, that's the image file that you could download from the FIMO website. That's the ternary diagram for the water dimer potential energy surface. So this is 2,500 geometries for 2 water molecules in all kinds of orientation, favorable and unfavorable. So we got everything that we need for a potential energy surface, so all possible angles. So as you see, there are some geometries where the electrostatic interaction is very favorable, like the hydrogen bonded geometry. There are some structures, some configurations where the electrostatic interaction is repulsive and very unfavorable. That's probably what would happen if I try placing these 2 water molecules like that. And there's everything in between. Do we cover the entire ternary diagram? We don't. It's quite interesting that we seem to be forming this band. And if you work out what it means to be on the band, it means that the other 2 components, so dispersion and induction, are approximately equal, so that you're at similar distances from the induction corner and the dispersion corner. Electrostatics can be everything from strongly attractive to strongly repulsive, but induction is kind of in between. Go ahead, Asta.
How is the induction and dispersion defined in
So it does include exchange induction, and induction includes Hartree-Fock delta.
Okay, so that's how you
Yes.
included everything.
Yes.
That's exactly there.
Yeah, I don't think that's a great strategy to just look at induction alone. So that's the way, like the way SAPT-0 split these terms. So that's induction is induction plus exchange induction plus delta Hartree-Fock. So it's still possible to get to the induction corner with ionic systems. So this great benchmark work by Rob DiStasio, the new data set, has a bunch of them. So there's a part here of the of this notebook that I'll probably skip, but I wanted to briefly tell you so that you can run it later, because I don't think there's anything to complete. So we run SAPT-0 so far, but it's actually possible to run some other SAPT variants, and as we talk, I can at least start running this for the water, and I'm running SAPT2 plus parenthesis 3. So SAPT2 plus parenthesis 3 is one of these higher order wave function based SAPT variants, so that we don't stop at E10 and E20, but we add things like E12 electrostatics, E13 electrostatics, we even add E30 dispersion. So we add more corrections, and that was actually pretty fast because that's a small system. Now, if you don't see a difference in the shape of this graph between SAPT-0 and SAPT2 plus parenthesis 3, I don't blame you for that, because honestly, I don't see a qualitative difference. I don't think our SAPT-0 was terrible. We will make a graph to compare, but it wasn't terrible. So that's the wave function based SAPT. Well, but we have other choices. We can run SAPT-DFT. For the small systems, SAPT-DFT will be a little bit slower than SAPT2 plus parenthesis 3. For bigger systems, SAPT-DFT is faster. But for SAPT-DFT, I need a little bit more input. So I need to set some additional options. So that part of the cell, the code, is quite important, because remember that if we want to run SAPT-DFT properly, we need to make sure that our exchange correlation potential is asymptotically correct. So that we need to shift the potential by the proper constant corresponding to the sum of the ionization potential and the HOMO energy. So I didn't calculate these numbers. What I usually do, I take the ionization potential from the NIST website, so the data set that has a lot of experimental numbers for different substances, and I calculate the HOMO energy using the same density functional as I use for SAPT-DFT, which in most cases is PB0. So I have these numbers here. Now I have two water molecules, so I have the same monomer for A and B, so I will use the same shift for molecule A and for molecule B. If you have two different molecules, you need a different asymptotic shift for A and for B. So the way I tell Psi4 what I want is by setting these options SAPT-DFT GRAC shift A and SAPT-DFT GRAC shift B. So Psi4 uses the GRAC asymptotic correction. It doesn't have Fermi-Abaldi program the other way, but it does have GRAC. And what it needs to know, because there's no default value, is what is the shift value for molecule A that I want to use and molecule B. And since molecule A and molecule B are both water molecules, I want to, I'm almost there. I want to use the same value. Now, this last slide is pure magic. Don't ask me why, but I somehow need to set it. So I know what it means, but I don't want to divulge on what it means. But it shouldn't be necessary, but it is. And so we did the same thing for the water dimer, and we ran SAPT-DFT. And honestly, it again looks similar. So I think I need some comparison, and I'll actually go and copy the code to make a graph, because that's, I think, quite useful for understanding how things work. We'll make a matplotlib graph of all of the different values for the water dimers that we have calculated. Well, I'll drop the Hartree-Fock because Hartree-Fock is probably the worst, but I'll plot coupled cluster, MP2, And so far, I've run 3 different SAPTs, SAPT0, SAPT2 plus parenthesis 3, and SAPT-DFT. So I have all this data, and I can make a graph. So none of these methods are terrible. The outlier here is SAPT0. So SAPT0 is not as accurate as the others, probably mostly because of the dispersion, and it's not uncommon for SAPT0 to be like overly attractive. But the other methods are really close. So as we said, we get lucky with MP2 for this system. I will just zoom in onto some of these. But really, we have overall a very good agreement between SAPT-DFT, SAPT2 plus parenthesis 3, MP2, and coupled cluster. It's not always like that, but I would say that for a large majority of closed shell complexes, both SAPT-DFT and SAPT2 plus parenthesis 3 are very trustworthy. And for the small system, SAPT2 plus parenthesis 3 happens to be faster, but definitely for bigger complexes, SAPT-DFT has a more favorable scaling. But both of these are available. So the last topic I wanted to bring up, and I gotta say that this is the cell that takes like up to 20 minutes, so don't worry if it, but I ran it before, so I have the file, so I'm cheating again, but I'll have it run in the background, so because we need a bigger molecule. So some functionality that is unique to Psi4, no other program has that, is something that tries to give you more insight into the interaction, especially between bigger molecules. And one of these variants is called functional group SAPT, or FSAPT. That's a brainchild of David Sherrill and his group. So SAPT, we use SAPT to, again, trying to avoid the word decompose, to represent the interaction energy as separate terms, to understand how much electrostatics, how much dispersion there is in the interaction between molecules A and B. With FSAPT, we can partition the numbers further, and we can try to understand for big molecules how much of the electrostatic energy between A and B comes from different parts of the molecule A and different parts of molecule B. We can do it only at the SAPT0 level. We cannot decompose like that some higher order SAPT, but I think it's a qualitative method. These numbers are not meant to be like rigorous and provide references. These numbers are meant to be useful. So in this example, of course, this FSAPT makes sense if we have bigger molecules than 2 others. So what I'm calculating is a phenol dimer. So that's why it takes more time. And in a phenol dimer, I can separate the hydroxyl group as one fragment and the phenyl group as the other one. And I can find out what part of SAPT in electrostatics, SAPT induction, SAPT dispersion is accounted for by the OH group and what part is accounted for by the ring. And at least the rigorous part of it is that the numbers will add up to SAPT0. So if I sum over all the fragments on A and all the fragments on B, I will get a given, if I sum the parts of electrostatics, I'll get the total SAPT electrostatic energy. So the way I run it, I define the complex. Now the 0, 1 is just like in Gaussian charge multiplicity. So I specify 2 fragments. I don't think I have to do that because that would be a default. But if I had an ionic fragment or a non-singlet fragment, I would specify that. So these are my two phenol molecules. I'll lower the basis set to June CCPVDC. And I specified a couple options, including the fact that I want to show some graphs. So I'll do that. And finally, I call Psi4 energy. Now, Fi SAPT0 might seem like a weird name, but it's the same code that does a couple different things, including FSAPT. So this calculation creates a subdirectory FSAPT under your current directory. It doesn't produce any output for you. So once you're done with this cell, you will only know by seeing a number in here. You will not see any specific output, but there's a script later on. a Python script that can be at a different location for your Psi4 installation, but if my Anaconda is there, that's where the script landed, and unfortunately I had to give the location where I tell how I fragment each of my molecule. Basically, I tell which atoms correspond to different fragments, and I will get the results separated by fragment. So maybe I'll actually stop this cell because I think I've went farther, so I should be able to run the next. You won't be able to run the next one until you finish that one because you don't have intermediate data, but I'm cheating here. I ran it before. So this is where it is. So I'm doing the SAPT script, which shouldn't take long. Forgot with it. It doesn't. Okay. This one didn't actually work, but I still have all the outputs. So basically, when you do an SAPT calculation, you run the post-processing script, you will get the file called, I think, fsapt.dat, and this is the kind of information that you get in the file. So you have fragment 1, fragment 2, and these were two phenols, so I separated each molecule into OH and phenyl, pH, and I get the SAPT terms: electrostatics, exchange, induction separately for AB and BA, dispersion, exchange. That's not exchange dispersion, sorry. This actually has exchange dispersion in it. That's the empirical dispersion if I ever wanted to include it, which I won't, and the total. So all is this line is just SAPT0. So I found that, for example, the dispersion energy between these two phenyl molecules is about negative 5.1 kilocalories per mole. And the biggest part of dispersion comes from two rings, which is not unexpected. These are bulky, and I guess it accounts for about half of it. And we'll take a look at the geometry. But the electrostatic energy in turn, of course, primarily comes from the interaction between two OH, which form a hydrogen bond in this structure. That's a hydrogen bonded structure of two phenol molecules, as we'll see. And it accounts for nearly all the electrostatics. So we can use SAPT to sometimes maybe understand a bit better what's going on in the interaction between two large molecules. We can decompose it further to see how much of the electrostatics or induction or dispersion is coming from some particular parts of the molecule. Now you have to be careful with how you cut the molecule. So in general, 3 rules: don't cut through aromatic rings, don't cut through any rings for that matter. I learned the hard way. And don't cut through double bonds, so multiple bonds. So here we cut the OH out, and that was fine. And I'll show you the SAPT script produces some PDB files with the numbers for different parts of SAPT that can be visualized. So total PDB is a file that was created with the decomposition of total SAPT interaction energy. Else PDB is electrostatics. And I'm using this ForteCube view code from Francesca Evangelista to show these molecules in the Jupyter notebook. So the nice thing is that I can rotate. You see the hydrogen bond between the two OH groups in this phenyl dimer. And here the color and the intensity of color means the overall contribution to the SAPT0 total energy. So this OH group, which is the acceptor of the hydrogen bond, accounts for the most of the attraction in this phenol dimer. Actually, this ring on this molecule on the right provides only repulsion. That's what the blue color means. And the intensity of the color means denotes the strength of the components. So the molecule A, I guess this OH is has a bit darker shade of red than the rest of the molecule, but overall, the contributions from both this OH group and this ring are attractive to the total interaction energy, but they are not as attractive as is this other OH group. So you see these kind of graphs in the several SAPT papers. So as you see, if you want these kinds of graphs, you can also visualize them in the notebook. And I did the total energy, but I can take a look at each part separately. So that's electrostatics. So electrostatics is the attractive electrostatics is dominated by the hydrogen bond, and the hydrogen bond is coming from this OH and this OH. So that's why this is the reddest. But if I change this to dispersion and rerun the cell, so first, well, dispersion is attractive between every part of the complex, and it's most red between the two rings. Now the color on these two OH groups is like pretty bland, and they don't contribute a lot to dispersion. Most of the dispersion is coming from the rings. So that's the kind of data you get from SAPT. And you might remember that we obtained these numbers by calling the energy for Fi SAPT. And this I there was weird. So what is it? So it turns out that there's also a possibility of using Psi4 to get some approximate decomposition of non-covalent interaction energies inside the molecule. There's a version of intramolecular SAPT, and that's actually something that my group has been working on a lot recently. And imagine that you have a molecule like this. Again, that's just an image file that is in your workshop GitHub site. So that's 2,4-pentane diol. So this diol has an intramolecular hydrogen bond. These two OH groups are interacting with each other. That's a favorable interaction. And I didn't draw two bonds in the molecule because in my method I'm planning to fragment the molecule. And the way intramolecular SAPT works is that you split the molecule into three pieces. So there's a fragment A, fragment B, they interact non-covalently, and there's a linker. The linker is C. So the linker has a covalent bond, one each, with A and B, and the parts of the fragments A and B interact non-covalently. So that's a specific setup, but how you fragment the molecule is your choice during the preparation of the input file. And of course, your results will depend on what fragmentation you decide on. But the capability that you have is calculating the electrostatics, induction, dispersion energy of fragment A interacting with fragment B in the presence of the linker. So, like, if the linker is far away and just connecting these parts of the molecule many angstroms apart, then it really doesn't make a difference physically if this is the same molecule or two different molecules. So we should expect kind of the same decomposition. And that's why we'd like to have the method that's able to give us energy contributions for an interactions that is still non-bonded, so non-covalent, like this hydrogen bond, but inside the same molecule. So we can run ISAPT. Now, due to some peculiarities, you have to specify the molecule in a slightly different form. So there's geometry, but you also have to tell where the fragments end and the multiplicities of the fragments. So I can, if you have more questions about it, I can definitely help out. But this part is actually well documented in the manual. This will take a couple minutes, but not super long. And this will calculate the interaction energy components between like this part and this part of 2,4-pentane diol. Definitely we expect to see the signatures of intramolecular hydrogen bond. So we expect, for example, attractive electrostatics. When I ran this calculation myself first, in I guess maybe around 2020, I was in for a huge disappointment. I got big repulsive electrostatics. And then we sat down, my grad student Du and I, to figure out what's going on, which was initially supposed to be a small side project, but ended up a full-fledged method development that now made it into Psi4 1.8. So we do some magic in this calculation that actually is denoted by this option, which I I did something wrong, and I'm not sure. Again, I ran things out of order. That's exactly because I stopped the previous calculation. Unfortunately, this didn't work out. So if you do things in order, it will work out. But I can get the Fi SAPT. The main psi4 calculation is, again, psi4.energy Fi SAPT 0. So I'm calling the same kind of energy calculation that before I used for functional group SAPT to decompose, to split the interaction energy between two molecules into the contributions from fragments. And now I use it for ISAPT, for intramolecular SAPT, to represent the interaction energy between fragments A and B connected by a linker C. And I actually generate a bunch of cube files with different quantities. For example, the stuff that I'm plotting here is actually electron densities on these fragments. So that's this 2,4-pentane diol, and I can plot using Francesco's Forte cube view code the density of fragment A, density of fragment B, and the density of the linker. It's pretty crucial to make the right decision of how you split these densities on the bonds that you break, because you can easily end up with unphysical dipole moments at these boundaries. That was exactly the source of our initial disappointment. That was exactly the problem that we had to solve. But here, this is how you can plot orbitals, densities, and of course, you do get numbers that are not rigorous by any means, because the splitting of the molecule into fragments is never completely rigorous, but they are useful. So again, there are some SAPT variants that are appropriate for reference numbers, and there's a lot of variants that are appropriate for quick and useful numbers, and there's more options. But first, we exactly use the allotted time that we have, and second, we run toward the end of our notebook. There's a bunch of further reading for you, and in case you missed completing some cells along the way, I'll be happy to help out with that, and I can answer some questions right now and many more questions afterwards. Yes, sir.
So I cannot unfortunately tunnel quickly there, but thank you very much for this fantastic tutorial. That was like a huge effort to make prepare all these materials. But I don't know, we have time for questions, or we should have a break.
I mean, I see Alston already has a hand up, so I'll let him ask the question.
That graph up, I wanted to just make a comment.
Okay.
Because you were precisely where you needed to be. I mean, what you didn't say, Conrad, is that all of those nice results which are close together are all wrong because of the basis set.
Absolutely.
Yeah, so that's something which has not been discussed because of time, but they all should be deeper by about 1 kilocal.
Exactly. Yes, we used the ADZ basis set for all our water calculations, and it still took a while for us. So I hope you understand why we didn't use AQZ. That definitely would give us deeper curves. But of course, if you wanted to run, the syntax would have been the same, and it's possible to, if you have a powerful laptop and power source and can wait, you can do that, but I would more likely to do that on a supercomputer.
Can I make one more comment? You don't need, I mean, this is something which is not well known outside the sub community, is that you don't need to necessarily go up to the main basis size. You can introduce mid-bonds. And Psi4 lets you use mid-bonds, but it's
Absolutely.
not included in the library.
You cannot do it from import Psi4? I didn't know that. I'll check.
Yeah, I use them. You don't use mid-bonds.
So I know that Psi4 got the support for mid-bonds kind of late, and I think it was thanks to you, because you kept bugging the developers and they relented. But for right now, so for the last 2 years or so, it is possible to run SAPT with mid-bonds, which is a great idea. I'm a big fan of mid-bonds myself, but it's a whole different story.
Okay, so